Dear students, in this video we are going to study about the capacitance and capacitance of a parallel plate capacitor, energy stored in a capacitor, applications of capacitor, effect of dielectrics in capacitors, capacitors which are connected in series and in parallel. Now let us study about capacitors and capacitance. First of all, let us see what is a capacitor. A capacitor is a device used to store electric charge and electrical energy. It consists of two conducting objects, usually plates or sheets, which are separated by some distance. Capacitors are widely used in many electronic circuits and have applications in many areas of science and technology. What is a capacitor? A simple capacitor consists of two parallel metal plates separated by a small distance as shown in this diagram. And these two plates are connected to a battery like this. So that's a parallel plate capacitor. And when this capacitor is connected to a battery of potential difference V, the electrons are transferred from one plate to the other by the battery, so that one plate becomes negatively charged with a charge of minus Q, and the other plate positively charged with plus Q like this. And the potential difference between the plates is equal to the battery's terminal voltage, and that is shown in 1.520 like this. If the battery voltage is increased, the amount of charge stored in the plates also will increase. So in general, we can store the charges in the capacitor, and that charge stored in the capacitor that will be proportional to the potential difference between the plates. Therefore, we can write the expression as Q directly proportional to V. That means Q is equal to CV, introducing this constant C, which is called the proportionality constant, and this C is called as capacitance. How to define this capacitance? For this, we can write this definition as the capacitance C of a capacitor is defined as the ratio of the magnitude of charge on either side of the conductor plates to the potential difference existing between them. That means C is equal to Q by V. What will be the unit of capacitance? That is, the SI unit of capacitance is given by Coulomb per volt or Farad. That is in honor of Michael Faraday. Farad is a very large unit of capacitance, and therefore in practice the capacitors are available in the range of microfarad, that is 1 mF, that is given by 10 to the minus 6 farad, to picofarad, that is 1 pF, that is given by 10 to the minus 12 farad. And how to represent a capacitor in a circuit? That is like this, two parallel lines like this, or like this also. And we should note that the total charge stored in the capacitor is 0, that means Q minus Q equals 0. And when you say the capacitor stores charges, it means the amount of charge that can be stored in any one of the plates. The capacitors are nowadays available in various shapes and types. That is like a cylinder or a disc. And the capacitors are made up of tantalum, ceramic, and electrolytic like this, represented in this diagram. Where these capacitors are used? These capacitors are widely used in various kinds of electronic circuits. Now let us see what is the capacitance of a parallel plate capacitor. For this, let us consider a capacitor with two parallel plates, each of cross-sectional area A and separated by a distance D as shown here. The electric field between two infinite parallel plates is uniform and is given by A equal to sigma by epsilon naught, where sigma is called the surface charge density on either place, that is given by sigma equal to Q by A. This charge per unit area, that is called as surface charge density. And if the separation D is very much smaller than the size of the plate, that is D square is very much less than A, then the above result can be used even for finite sized parallel plate capacitor. So here is a capacitance of a parallel plate capacitor. So what will be the electric field between the plates? That is going to be E equal to Q by epsilon naught A. Since the electric field is uniform, the electric potential difference between the plates having a separation D is given by V equal to ED, that's equal to QD by epsilon naught A. Therefore, the capacitance of a capacitor is given by C equal to Q by V or Q by QD by epsilon naught A, and that's given by epsilon naught A by D. So from this equation, it is evident that the capacitance is directly proportional to the area of cross-section A and is inversely proportional to the distance d between the plates. So that can be understood from the following points. That is, first point is, if the area of cross-section of a capacitor plate is increased, more charges can be distributed for the same potential difference. Therefore, the capacitance is increased. And the second point is, if the distance d between the two plates is reduced, the potential difference between the plates V is equal to ED decreases because d. As a result, voltage difference between the terminals of the battery increases, which in turn leads to an additional flow of charge to the plates from the battery till the voltage on the capacitor is equal to the battery's terminal voltage. Suppose the distance is increased, the capacitor voltage also increases and becomes greater than the battery voltage. Then the charges will start flowing from the capacitor plates to the battery till both the voltages are equal. Here in this video, we have a capacitor, parallel plate capacitor separated by a distance of 5 millimeter and area of cross section of 100 millimeter square. And here is a battery for which the voltage is about 1.5 volts, which we can verify by using a voltmeter. The positive is connected to this positive plate and the negative terminal is connected to the negative plate. So this voltmeter shows 1.5 volts, and for this separation we have the capacitance that is about 1.77 10 power minus 13 farad. Now let us see if the distance of separation between the two plates is varied. Let us see what happens to the capacitance. We see here the distance is increased to about 10 millimeter, and so the capacitance is reduced to 0.89 10 power minus 13 farad, as the distance is in the denominator, epsilon naught A by D. And if you vary the area of this capacitor like this here, as the area of a parallel plate capacitor is increased, the capacitance also increases. Similarly, the plate charge at the top, that is also maximum, and the stored energy is also maximum. So we can vary this area of a parallel plate capacitor and also the distance between the two plates. And this shows the electric field lines like this. Now we will study about energy stored in a capacitor. A capacitor not only stores the charge but also it stores some energy. When a battery is connected to the capacitor, electrons of total charge minus Q are transferred from one plate to the other plate. To transfer the charge, work is done by the battery. This work done is known as electrostatic potential energy in the capacitor. To transfer an infinitesimal charge dq for a potential difference V, the work done is given by this expression dW equal to V dq, where this V is given by the ratio of the charge to the capacitance of the capacitor. The total work done to charge a capacitor is given by this expression W equal to integral 0 to Q of Q by C dq. Thus, we will get the expression as Q squared by 2C. This work done is stored as electrostatic potential energy in the capacitor. So, UE is given by Q squared by 2C, that's half CV square, as Q is given by C times V. Q equal to CV is used. This stored energy is thus directly proportional to the capacitance of the capacitor and the square of the voltage between the plates of the capacitor. But where is this energy stored in the capacitor? To understand this question, the equation on page 7 is written as C equal to epsilon A by D and V equal to E times D. U is given by half epsilon A by D into ED square, that's equal to half epsilon AD into E square. So this AD is the volume of the space between the capacitor plates. And therefore, the energy stored per unit volume of space is defined as the energy density, UE, and that's given by U by volume. So from this equation 1.88, we have UE equal to half epsilon naught E square. And from this equation 1.89, we infer that the energy stored in the electric field existing between the plates of the capacitor. Once the capacitor is allowed to discharge, the energy is retrieved. And it is very important to note that the energy density depends only on the electric field and not on the size of the plates of the capacitor. So in fact, this expression 1.89 is true for the electric field due to any type of charge configuration. Now let us study about the applications of capacitors, where these capacitors are used in our daily life. Capacitors are usually used in various electronic circuits, and a few of the applications are given below. So here in this case, first case, flash capacitors are being used where? That's in digital cameras for taking photographs. The flash which comes from the camera when we take photographs is due to the energy released from the capacitor, and that's called a flash capacitor. That's given in 1.55a here. So this is the flash capacitor present in a camera. Next, during cardiac arrest, a device called heart defibrillator is used to give a sudden surge of large amount of electrical energy to a patient's chest to retrieve the normal heart function. So that's given here. In the next case, the capacitors are used in the ignition system of automobile engines to eliminate sparking that you should have seen in two-wheelers to start the vehicle. Next one is the capacitors are used to reduce power fluctuations in power supplies and to increase the efficiency of power transmission. However, the capacitors have also some disadvantages. Let us see what's that. Even after the battery or power supply is removed, the capacitor stores charges and energy for some time. For example, if the TV is switched off, it is always advisable not to touch the back side of the TV panel because you can get a severe shock. Next, we are going to study about the effect of dielectrics in capacitors. In earlier discussions, we assumed that the space between the parallel plates of the capacitor is either empty or filled with air. Suppose the dielectrics like mica, glass, or paper are introduced between the plates, then the capacitance of the capacitor is altered. The dielectric can be inserted into the plates in two different ways. First one, when the capacitor is disconnected from the battery, and second one is when the capacitor is connected to the battery. Let us consider the first case when the capacitor is disconnected from the battery. For this, let us consider a capacitor with two parallel plates, each of cross-sectional area A, and are separated by distance D. The capacitor is charged by a battery of voltage V0, and the charge is stored as Q0. The capacitance of the capacitor without the dielectric is given by this expression C0 equal to Q0 by V0. The battery is then disconnected from the capacitor and the dielectric is inserted between the plates, and that's shown in this figure 1.56. The introduction of dielectric between the plates will decrease the electric field. Experimentally, it is found that the modified electric field is given by this expression E is equal to E0 by epsilon R. But this E0 is the electric field inside the capacitor when there is no dielectric, and epsilon R is the relative permittivity of the dielectric, or simply known as the dielectric constant. And since epsilon R is greater than 1, the electric field is given by E is less than E0. As a result, the electrostatic potential difference between the plates V is equal to ED is also reduced. But at the same time, the charge Q0 will remain constant once the battery is disconnected. Hence, a new potential difference is given by this expression 1.92, that is V equal to ED, or V0 by epsilon R. We know that the capacitance is inversely proportional to the potential difference. Therefore, as V decreases, C increases. Thus, the new capacitance in the presence of a dielectric is given by this expression, that is C is equal to epsilon R times C0. Since epsilon R is greater than 1, we have C is also greater than C0. That means if you insert a dielectric between the two plates. That will definitely increase the capacitance value. So using this equation C equal to epsilon R A by D, where this epsilon R is given by epsilon R times epsilon R. This is the permittivity of the dielectric medium. The energy stored in the capacitor before the insertion of the dielectric is given by this expression U naught equal to half Q naught squared by C naught. After the dielectric is inserted, the charge Q naught remains constant, but the capacitance is increased. As a result, the stored energy is also decreased. Now, U is given by U naught by epsilon R, and since epsilon R is greater than 1, we get U is less than U naught. There is a decrease in energy because when the dielectric is inserted, the capacitor spends some energy in pulling the dielectric inside. Now let us consider the second case when the battery remains connected to the capacitor. Let's now consider what happens when the battery of voltage V0 remains connected to the capacitor when the dielectric is inserted into the capacitor. That's given in 1.57 here. So the potential difference V0 across the plates remains constant, but it is found experimentally, that is, when the dielectric is inserted, the charge stored in the capacitor is also increased by a factor of epsilon R. Now here, the expression is given by T equal to epsilon R times Q naught. And due to this increased charge, the capacitance is also increased. So the new capacitance has a value given by this expression C is equal to epsilon R times C naught. However, the reason for the increase in capacitance in this case when the battery remains connected is different from the case when the battery is disconnected before introducing the dielectric. So we get these two expressions, epsilon naught is equal to epsilon A by D and C is equal to epsilon A by D. The energy stored in the capacitor before the insertion of a dielectric is given by this expression 1.100, that is U naught equal to half C naught V naught square. Here we should note that we are not using the expression U naught equal to half Q naught square by C naught, because here both charge and capacitance are changed, whereas in this equation 1.10, V naught remains constant. So after this dielectric is inserted, what happens to the capacitance? Actually, it will be increased because the stored energy is also increased. So U is given by half C naught square, that's given by epsilon R times U naught. Since epsilon R is greater than 1, we can have U also greater than U naught. It may be noted here that since voltage between the capacitor V naught is constant, the electric field between the plates also remains constant. And the density is given by U is equal to half epsilon E square, E naught square here. So this epsilon is the permittivity of the given dielectric material. And the results of the discussions are summarized in the table 1.2. Here it is given how a computer keyboard keys are working. Next, we are going to study about this effect of dielectrics in capacitors. In this case, the dielectric is inserted when the battery is disconnected and when the battery is connected. What happens to the charge, voltage, electric field, capacitance, and energy. Next, we are going to study about the capacitors which are connected in series and in parallel. In the first case, let us study about the capacitors which are connected in series. In this case, there are three capacitors of capacitance C1, C2, and C3 which are connected in series with the battery of voltage V. As soon as the battery is connected to the capacitors in series, the electrons of charge minus Q are transferred from negative terminal to the right plate of C3, which pushes the electrons of same current minus Q from the left plate of C3 to the right plate of C2 due to electrostatic induction. Similarly, the left plate of C2 pushes the charges of minus Q to the right plate of C1, which induces the positive charge plus Q on the left plate of C1. At the same time, electrons of charge minus Q are transferred from the left plate of C1 to positive terminal of the battery. By these processes, each capacitor stores the same amount of charge Q. The capacitances of the capacitors are in general different, so that the voltage across each capacitor is also different and are denoted as V1, V2, and V3 respectively. So from this expression it is noted that the sum of the voltages across the capacitor must be equal to the voltage of the battery. So V is given by V1 plus V2 plus V3. And since Q is equal to C, we have V equal to Q by C1 plus Q by C2 plus Q by C3. That's given by Q, as this Q is common, that is the charge present in the capacitor. Q into 1 by C1 plus 1 by C2 plus 1 by C3. So if these three capacitors in series are considered to form an equal and single capacitor, CS, as shown in the diagram, then we have V equal to Q by CS, this one. Substituting this expression in the equations 1.104, we get this expression 1.105. That's 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So the inverse of the equivalent capacitance CS of three capacitors connected in series is equal to the sum of the inverses of each capacitance. So this equivalent capacitance CS is always less than the smallest individual capacitance in the series. Next we are going to study about the capacitors which are connected in parallel. For this, let us consider three capacitors of capacitor C1, C2, C3 which are connected in parallel with a battery of voltage V, as shown in 1.59a. Yeah. And since the corresponding sides of the capacitors are connected to the same positive or negative terminals of the battery, the voltage across each capacitor must be equal to the battery's voltage. Since the capacitance of the capacitors are different, the charge stored in each capacitor is not the same. So the charge stored in the three capacitors can be written as Q1, Q2, and Q3 respectively. According to the law of conservation of total charge, the sum of these three charges is equal to the charge Q transferred by the battery. So we can get the expression as Q equal to C1V plus C2V plus C3V. If these three capacitors are considered to form a single equivalent capacitance Cp, which stores the total charge Q as shown in the figure 1.59b, like this. Next, we can write Q equal to Cp times V. Substituting this equation, we get the expression as Cp times Cp into V times, that's given by C1V plus C2V plus C3V, and simplifying we will get Cp equals C1 plus C2 plus C3, as we can be cancel on both left hand side and right hand side. Next, we are going to study about the equivalent capacitance. What is that equivalent capacitance when the capacitors are connected in parallel? So the equivalent capacitance of capacitors which are connected in parallel will be equal to the sum of the individual capacitance. The equivalent capacitance Cp in a parallel connection is always greater than the largest individual capacitance. So in a parallel connection, it is equivalent as area of each capacitance. As to give more effective area, such as total capacitance increases.